My project is called the Billiard Problem, and it's about chaos. So it's a little bit like the pendulum problem we did before in the semester, in that it starts out with a motion that's simple and harmonic and predictable over long periods of time. And as you add more factors to even a pretty simple system, it starts to become very chaotic and unpredictable, even though it still follows the laws of physics. So chaos theory, just to review, I know we've already had this in the semester, but according to the Britannica Encyclopedia, it is the study of apparently random or unpredictable behavior in systems governed by deterministic laws. So to me, this means that these systems still follow the laws of physics. They still fit a lot of the models that we know about, but their behavior over a long period of time is very random and unpredictable and difficult to study. So applications of chaos theory include things like the stock market, the human body with all of its complex systems and interactions, safety testing over long periods of time, like in things like airplane engines. The weather is a huge example of chaos theory. And even there's a lot of circuits where they're nonlinear circuits, and even very simple ones where one system is driven by the other can create a lot of chaotic behavior. So I got this idea from a great textbook that Dr. Cornell recommended. It's called Computational Physics by Nicholas J. Giordano and Hiyasu Nakanshi. It's a great book, though. It details this billiard problem that I'm about to describe and talks a lot about chaos theory. So this isn't quite a normal billiard table. Here, I'm going to comment out these lines that we might use later. So if I show you, it's basically just a ball moving frictionlessly throughout this surface, and every collision is perfectly elastic. So it's a very simple system. There's no friction. There's no complications with the collisions. And it's in a simple shape, like this square here. So you can see over long periods of time, this would create a pattern that would repeat itself over and over. And we'd be able to predict, in 5 minutes, in 10 years, exactly where this ball is going to be in this very isolated and simple system. Another shape here, the circle, where we have two balls moving here, and one ball started a slightly different trajectory than the other one. And even though they're moving at slightly different trajectories, because they're in this simple shape, in this very isolated system, again, no friction, perfectly elastic collisions, they follow just about a similar path. You can see, as we make it just slightly more complicated, we've seen the circle and the square, and we can put them together in a shape that the book calls the stadium shape. Here you can kind of see why it kind of looks like a stadium. Even though these balls, you can see they started with a very similar trajectory, but immediately their trajectories start diverging. They start getting really, really different and very unpredictable over long periods of time. So now I want to focus on these graphs here. If we want to go back to the square, let me uncomment these lines again. If we run this program, you can see they start on slightly different trajectories, but they basically both follow these predictable patterns, these predictable movements that kind of end up being pretty similar over long periods of time. So you can see in this graph right here, these are two phase space diagrams that are just velocity versus position x. And for a square, those are very boring. But the separation graph here, what this is the difference between the x positions of these billiard balls plotted over time. So this is a lot like, we had a graph like this in the pendulum problem, where we compared the two theta values of the pendulums, and where these cross, where their positions are very similar, you can see these dips. But overall, you can tell that it's not very far above zero. They're moving on pretty similar paths, and it's getting more similar. You can see like it's kind of moving down. As we went over with the pendulum project, the Lyapunov exponent, that's basically the slope of this trend right here. So this slope, they're trending downward, which means they're getting less chaotic. They're predictable, and they'll end up on kind of a similar path. We can see a very similar thing here with the circle, where they start slightly different trajectories and they basically stay slightly different trajectories. You can see they're tracing a similar path. And this graph here that shows the difference between them, kind of a measure of how chaotic the system is, really. They're it's staying right around zero. It's trending downwards. It's a very predictable system because it's so simple. So we can see even the two phase space diagrams, very, very similar. So if we go over to the stadium shape and we start running it, you probably noticed this before. The separation graph here, like it'll eventually, as we let it keep running, it'll keep trending upwards, which means it's getting more and more chaotic. The more it trends upwards, it basically means the more like it means that the trajectories are very different. They're getting more different as time goes on. So like it's a way of showing graphically that even though they started with only slightly different trajectories to begin with, as time goes on, they end up on very, very different paths. And this is really interesting because, obviously, the computer is able to simulate this, so it's not completely unpredictable and random. It still follows the laws of physics, but over time we really can't predict it. So the book kind of describes these things as a paradox of being both predictable and deterministic, meaning they're unpredictable, but they still follow the laws of physics, and it's kind of a paradox. Then these things happen in real life, like the weather, the motions of the clouds. Even things in engineering that are supposed to last for a long time. You don't know what's going to happen to them. You don't know what a car is going to go through in its whole lifetime. And this is one of the big reasons why we need computational physics, why computers are so important to the study of physics, is because you can't really model these systems mathematically. You can't really look at the weather patterns of the Earth and say, okay, what is this going to be like in 30 years and do it on a blackboard. It doesn't really work that way. So we need these computers to be able to make these deterministic calculations based on each condition that the system finds itself in, so that we can kind of begin to model these things. So that's, I guess you can see here in this project that even in a very simple, very isolated system, we can see chaos happening where things are deterministic and unpredictable at the same time.